In this video, we're going to be taking a look at vector addition and applying them to electrical circuits, specifically dealing with the voltages within a circuit. What are we going to do? We're going to be applying vector addition to the voltage changes in an electrical circuit. Why are we doing this? Because voltage gains and losses in a closed circuit follow the principles of vector addition that makes it much easier to work with. We're also going to reinforce what we know about vector addition through this type of activity. Also, this property of vectors will lay down the foundation for various important electrical rules about voltages as well as current that we'll see throughout the year. Electricity in circuits is an abstract concept for most people because we don't actually see what's going on inside the circuit. And that takes time for people to understand what's going on. By working on electricity throughout the year, we will now have that time to develop a good understanding of what's going on. Also, this runs in parallel with the concepts of vectors and forces that we'll be learning throughout the year. So this connection will also form a physical and visual connection that you can use to help understand what's going on in the abstract systems. So in the past, we've compared a circuit to a factory shipping packages off to various businesses. The factory is a lot like the battery, where the factory provides a product to the various businesses. The businesses are like the resistors. The product in this case is energy. The energy that the charges have is similar to what the product that the factory would offer to the various businesses, because the energy is going to be transported to the resistors or the motors or the lights or whatever. The trucks are like the charges that carry the desired packages. So the charges carry the energy from the battery. The amount of energy carried by a single charge is known as the electric potential. Now, when our trucks leave the factory, they are packed full of boxes. When our charges leave the battery, they are packed full of energy, so they have a lot of electric potential. As the trucks travel to the businesses, they will drop off packages. Trucks going through this route will drop off to 2 businesses and return empty. Charges that travel through this route will also drop off to 2 resistors and then return with no electrical potential. Any truck that travels this route will drop off to 1 business. So they will drop off their entire load to this one place, just like any charge that travels through this light bulb will drop off its entire electric potential load. So it will then return with no electric potential. Because truck drivers who return with boxes in their truck get fired. They weren't hired to drive packages around the town. They were hired to deliver them to places. So same thing here with the circuit. Now the term voltage refers to the change in the electric potential that a charge has. So it's not something that a charge actually possesses. It's how much it changes by. So when we turn around and say we have a 9-volt battery, we're saying that this battery increases the electric potential of a charge by 9 volts. And if a charge passes through a resistor and we find out that the resistor has 6 volts, it doesn't mean that the charge has had 6 volts. It means that it had dropped off 6 volts. So a charge could be entering with 10 volts and leaving with 4 volts, and the difference being 6 is what was left with that resistor. So voltage is always a change in the potential energy per charge. It's not actually the amount of energy there. Something that a lot of people get confused on constantly. Voltages, in a way, really have 2 directions. Positive up if something increases its voltage. For example, a battery would have a positive voltage as it increases the electric potential of the charges. and down being negative. So if something was to decrease their energy, for example, a motor or a resistor would actually be negative because that's going to actually lower the electric potential of the charges because they're using up their energy. The resistors are using up the energy to do whatever it is that they need to do. The resultant of an entire circuit, the resultant voltage for the entire circuit would be the sum of all the voltages of the batteries plus all the voltages of the resistors. So all the batteries giving energy to the charges and all the resistors using them up. Now, if I have a closed loop, that means the total voltage of the entire circuit added up has to be zero in the end. So whatever the battery gives has to be used up by the resistors. Knowing that, we can easily solve a question that's fairly basic, where I have two resistors, each 2 volts each, connected in line with each other, that is then connected to 3 resistors all in one loop. The first light bulb gets 1 volt, the second light bulb gets 2 volts, and I want to know what the voltage of the third light bulb is. Now, some of us might already instinctually come up with an answer, and if you're thinking that's probably 1, you're probably correct. But how do we get to that answer? And understanding the process to get that is key for understanding the complicated questions that will soon follow. So if I think of this as a closed loop, and it is because there is no gaps whatsoever, and I think of a charge that starts right over here, it would get voltage from this battery, voltage from this battery, and then it would have to lose voltage to each of the light bulbs. So I'm going to turn around and say that the voltage of each object, the 2 batteries, and the 3 light bulbs all have to add up to 0. I can now solve for the unknown voltage by simple algebra. So the voltage of the light bulb equals the summation of the opposites of all the other voltages. If I'm doing this as a vector, since voltages have a direction of both up and down, positive or negative, I can then set up a scale saying 1 box is equal to 1 volt, and I can now simply draw out the vectors for negative V1. Well, negative V1 would be 2 in the down direction because V1 was positive 2. After that, I can now draw out my second vector, tip tail. So at the end of the first vector, I draw out my second vector. And again, this guy was 2 volts. And so my box length would be 2. And since it's the opposite of up, it's going to go down. My next one would be 1. So if I now draw that one out tip to tail, I would have 1 going up because it's the opposite of down. This one here is 2, so that would be going up because that's the opposite of down. And please notice each vector is tip to tail. I can now go ahead and solve for 5, which would then be my resultant. So going from start to finish, I can see I have a vector that is 1 box in length going down. So this means, based on my scale, the voltage of this third light bulb is negative 1 volts. We could also solve this problem through simple algebra. Since the voltages only have 2 directions of up and down, positive or negative, we could actually solve this as this regular algebraic equation without using vectors. So I could turn around and say that the total resultant voltage of change in voltage 1, well, change in electric potential 1, or voltage 1 plus voltage 2 plus voltage 3 plus voltage 4 plus voltage 5 equals 0. And then I can turn around and say for the batteries, I have positive 2 volts and positive 2 volts plus negative 1 plus negative 2 volts plus the unknown, and simply solve. And basic algebra gives me negative 1 volts. Now, this is very important because the answer here is very important in the fact that we will often phrase this in a positive answer. The reason for that is the charges in the circuit have lost 1 volt. That's the perspective that we've done here. The charges in the circuit have lost a voltage to the light bulb. However, if we are interested in what the light bulb receives, and a lot of times when we ask for what's the voltage of the light bulb, we're actually looking at this from the light bulb's perspective. We're going to say it's a positive voltage. And that's because with one thing loses, the other thing gains. The circuit lost 1 volt. The charges lost 1 volt. But that's because that volt went into the light bulb. It went into the resistor. And so a lot of times when we ask for what's the voltage of the light bulb, it's going to be a positive answer, which confuses people a lot of times when we're doing our work, because when we actually solve for things, it'll be a negative answer and will be a negative number. And that's because we're looking at things from a circuit perspective. So this is one of those things that will often confuse people, because you'll have to be clear on which perspective that you're using and why you're using that perspective. And again, that will take time, so we have time to work on that. We can also think of a circuit as, if you will, a water slide, where the battery acts like the ladder, where people go up the ladder gaining potential energy. And so the charges, as they are traveled through the battery, gain electric potential. The charges then go down the slide, and every drop is like a resistor. In some slides, we might have multiple smaller drops. In other sections, I might have a large drop. Bottom line, though, is the overall change in the distance dropped for each slide is literally the same. It's just how you get there. But that's something we're going to work on later on in the year. Once again, this is all just to introduce what we're working on. So if you kind of get this, you're in a very good spot. If you understand this completely, you are well ahead of the game. This is something that we'll have to really have down later on after the Christmas and winter break.